All right, here we go. This is problem number 16 from chapter 9 of the Holiday and Resnick textbook. We got Ricardo and Carmelita sitting in a canoe, and they switch places. And based on the fact that the canoe moves 40 centimeters, we got to find Carmelita's mass. All right, so here's the deal. It sounds like this question might not be worded very well. Some people have had some complaints about it, but so here's the deal. So here's the canoe, right? Okay. Now, it tells us that Ricardo and Carmelita are 3 meters apart and symmetrically located with respect to the canoe's center. So let's assume that our canoe is uniformly distributed. So that X there represents the center of mass of the canoe. Okay? Now, Ricardo's at one end. So here's Ricardo, and here's Carmelita. Carmelita, right? Now, it tells us that Ricardo is heavier than Carmelita. So that means that the center of mass of our system is going to be a little bit closer to Carmelita, all right? So here's what I'm going to do. I think this will make things a little bit easier to visualize, all right? So the Ricardo canoe Carmelita system has a center of mass that's closer to Ricardo. So let's put, it talks about this pier post. Let's pretend that the pier post is lined up with the center of mass of the Ricardo canoe Carmelita system. All right. So the idea is then that based on that, remember, so what's going to happen is they switch places, right? So Ricardo is going to walk over here. Carmelita is going to walk over here. Oops. And, you know, those are going to be internal forces, right? As Ricardo walks to the right, he's going to be pushing the canoe to the left. As Carmelita walks to the left, he's going to be pushing the canoe to the right. And so the canoe is going to move, okay? But remember, the velocity of our center of mass is got to be zero, right? Because we don't have any external forces. All of the forces are coming from either Ricardo or Carmelita, all right? So the idea is the canoe is going to move. So let's draw our canoe. Oh, darn it. Let's draw our canoe again. So after they switch places, here's our canoe again. Still 3 meters long. But the issue is now Carmelita's sitting on this end and Ricardo is here, right? Okay. And here's the center of mass of the canoe. Well, remember, the center of mass of this green dot, I'm sorry, the velocity of this green dot, which represents the center of mass of the whole system, can't have moved. So the center of mass of my system now is going to be right about here, right? Oh, well, that means that the post must be here. Okay? So what that's basically telling us is that the canoe has moved left. Okay? Which makes sense because Ricardo has more mass, so he's going to sort of produce more force walking forward than Carmelita does. A little sloppy, but basically that's the idea. Okay? So let's see if we can do some calculations here. So what we know is we know that this canoe moved 40 centimeters this way. All right, so here's what I'm going to do. We need a number line here. What color haven't we used yet? We haven't used purple yet. So let's call this, we'll call this a position as 0. All right, so the center of mass couldn't have moved. So in this first drawing, the position of our center of mass is going to be this. It's going to be Ricardo's mass, 80 kilograms, times his position, which is 0, plus the canoe's mass, 30 kilograms, times its position. Remember, they're 3 meters apart, and the center of mass of the canoe itself is between them. So that's going to be at a position of 1.5 meters, plus the mass of Carmelita, times her position, which is 3 meters, right? Okay, and then all of this is going to be divided by 80 plus 30 plus the mass of Carmelita. All right, so that's before they walk. Now, after the motion, let's use orange. After they move, the position of our center of mass is going to be this. Well, let's see. Our whole thing has moved to the left 40 centimeters. So what that means is this is where x equals 0 is, and everything is moved this way 40 centimeters. So that means Carmelita's position is now negative 0.4, right? So we're looking at the mass of Carmelita times her position, which is negative 0.4, plus 30 kilograms for the canoe. It was at a position of 1.5, but it moved to the left 1.4, so now we're at 1.1. And Ricardo's at the other end of the canoe, which has moved, so 80 kilograms for Ricardo. But the other end of the canoe is now at a position of 3 minus 0.4, so 2.6. All over 80 plus 30 plus the mass of Carmelita. So then all I'm going to do is I'm going to set these two fractions equal to each other. But it ends up not being bad because they have the same denominator, so your denominators cancel. Alright, so let's see what our expression is then. We're going to have this. 80 times 0 is 0. 30 times 1.5 is 4.5. No, it isn't. It's 45. So that's 45 plus 3 times the mass of Carmelita equals negative 0.4 times the mass of Carmelita plus 30 times 1.1 is what, 33? Plus 80 times 2.6 gives us 208. Oops, 208. Alright, so let's solve this mess. Let's see what we get. Let's see, so I'm going to add 0.4, so it looks like we're going to get 3.4 times the mass of Carmelita equals 33 plus 208 minus 45. So 3.4 times the mass of Carmelita equals 33 plus 208 minus 45 gives us 196. So divide that by 3.4. And we get that the mass of Carmelita, it turns out to be 57.6, so let's just round it up to, 58 kilograms. There we go. All right.